So let's start. So as a reminder, 2 days ago, we covered applications of AI to measuring learning and modeling learning, so how students learn over time. And we saw some AI topics from before, which were machine learning and search. Today, we're going to look at assessment, so applications of AI to assessment. And the AI topics that we're going to mostly focus on are, again, application of machine learning and a little bit of mechanism design, which you have on your homework. So let's just dive in. So as an overview of today, first we're going to talk about item response theory. And just as a show of hands, how many of you have seen or know what item response theory is? Nobody. OK, that's great. And then we're going to talk about an application of that, which is computerized adaptive testing. And finally, another application, which is a recent paper actually from last year, on calibrated self-assessment. So let's dive into item response theory. So as a reminder, last time we talked about this AFM, or additive factors model, which is a logistic regression model. And we saw how it has multiple parts. So just my cursor here. So theta sub I was the ability of the student. So we're trying to measure a student's learning over time. Theta sub I was the ability of the student. We had this Q matrix here, which mapped different questions to skills. So for example, if we had a problem that was like A times B plus C, that would have a multiplication skill and an addition skill. So, and then for each skill, we had this beta parameter, which was sort of the intercept, or we can think of it as the difficulty of skill K. And we had this GEM parameter, which was the learn rate for skill K, and then the number of opportunities. So as a student does more opportunities, presumably their error rate should go down, and their performance should increase. OK, so hopefully that's familiar to all of you. So now I have a question. How would we modify this model? So now let's say we don't want to model student learning, but we want to model a student's ability as they're working on a test. Right? So they're doing a test, and we want to try to measure how well the student is doing on the test. So how might we modify this model for that setup? Basically, the question is, what's different between learning and testing, I guess? Like a student in a learning environment versus a student in an environment where they're taking a test. Sorry, who's? Yeah?
You only get feedback. Or in the testing scenario, you only get feedback after you looked at all the questions, as opposed to learning where you get feedback after every question.
OK, great. So how will that impact the model? Any ideas? T would be 1. OK. What's a better way to modify it? That's the right idea. What's a better simplification we can do than just set T to be 1? I mean, you could just get rid of T altogether, right? You could just get rid of this term. Because we're assuming no learning, so why do we have a learning rate? So this is something I didn't talk about last time, which is that you mentioned, which is a great point, that we assume that when a student is in a learning environment, after they do each problem, they're getting some feedback. And that's how they're learning. Now, you might say that students are able to learn even without feedback. But the general assumption that's made is that if you give a student feedback, they're going to learn from it. And if you don't, they're not. So we're just going to stick to that assumption. So otherwise, when you're taking tests, that means like every problem you do, you're learning from it. So you can then you can go back and do that problem again and then improve your score. So which typically doesn't happen. Huh? It could.
Yeah, if you don't know what you're doing, that's what happens.
But then, OK, so you could learn during the test. That probably means you're remembering things you've learned before, though. Right? No, and I'm not saying that this assumption is completely accurate. You might learn in some settings, but we're assuming you don't. Yeah.
What's the meaning of
The meaning of Q sub jk?
Yeah.
So we assume you have a set of items, j, which are different problems, and a set of skills, k. And Q sub jk is 1 if that item includes that skill. So if the skill, like for example, you have the problem A times B plus C. Multiplication is a skill in that problem. So you have this matrix, and in that matrix, the cell corresponding to the column of skill multiplication and the item A times B plus C would be 1. But for the skill division, the matrix would say it's 0. So it basically says which skills are part of this problem. And we're only measuring the learning for those skills. So any skill that's not in the problem, we're assuming no learning takes place.
So QJK has to be binary or not?
Yes. Q matrix is always binary. Good question. Okay, we're going to make one other simplifying assumption. That's to get rid of this Q matrix altogether. So the model we're going to look at, so this is an item response theory model. There's several models. The first one's the one parameter model. In this model, it's much more simple. So we're sort of going back. We're simplifying things a lot. We're going to assume that each item, you don't decompose an item into different skills, which we assumed in the additive factors model. We're going to assume an item has only one skill, and that's a one-to-one mapping, basically. So going back to your question, don't worry about the Q matrix for this lecture. There's no Q matrix. Now, if you had a Q matrix, there's another model called the linear logistic test model, something like that. But item response theory is a much more common model that's used in testing settings. And this model comes from the psychrometrics literature, which is sort of like a intersection of psychology and statistics. So it's like people looking at how to do testing from a psychological perspective. Yeah. So this is the one parameter item response theory model. And it's sort of confusing because we say one parameter, but there's sort of two parameters. There's the theta parameter and the b parameter. B is exactly what beta was before, except that beta here was for a skill. B now is just for an item. So it's b sub j. Okay? So b is the difficulty of item j, and theta is the ability of student I. One nice thing about this model is that the ability of a student is sort of on the same scale as the difficulty of every item. So you're saying, which makes it sort of nice for interpretation, as we'll see soon. And so here, these are just the two different ways to express this model, right? This is the standard logistic form. This is where we equate the log odds to sort of a linear equation. Right? So does this model make sense? So basically, we say if we give item j to a student, the item has some difficulty, and the student has some ability. And if you simply take the subtraction of the student's ability and the item's difficulty, then you get sort of the log odds of basically of the student succeeding on that problem, student answering correctly. Or in other words, if you take the logistic function of the difference between the student's ability and the item's difficulty, you get the probability that the student would answer the item correctly. Does that make sense? Yeah.
So your students can't be better at some tasks and worse at other tasks.
It's a very good point. This seems like an oversimplification to me, because yes, you would assume that some students, like maybe they study for a certain type of problem, so they're better at that problem and not at other problems. So you might think that theta should depend on I and j, for example. That there should be a student ability for each item, right? And again, what's one reason you wouldn't want to make that modeling decision?
You need a lot of data for that?
Yeah, you'd need more data to fit this model, because then you'd have many parameters. You'd have many parameters for each student, right? So this is sort of a simplifying assumption that makes sense from a modeling perspective. And presumably there's some justifications in the psychometrics literature for why it makes sense from a psychological perspective. One idea would be that students have some latent ability, and that ability really, and this is actually what's measured, for example, when you take the SAT or the GRE or any of these exams, you're given one score at the end. Well, for all tests, you're typically given one score, but it really only gives you one score, and that's sort of a measure of your ability, and that's what they care about. But that doesn't mean that your ability is the same for every problem, and it follows this model. So it is sort of an oversimplification, I would say. But it might come from that idea that they really want people who work in these testing environments, like the Educational Testing Service, which gives the GRE and the SAT and all these tests. They really want to measure some latent ability of some topic, whether that's like verbal ability or math ability. But the second reason, I guess, would be because from a machine learning perspective, you don't want to have many parameters. Okay, well, that was a very good question. Okay, so we can modify this model a bit. There's a there's a typo there. The two parameter should be 2PL IRT model. And the parameter that we're adding here is this A sub j. And this corresponds to the discrimination of item j. So what this means is that different items have a different ability to discriminate between different students. What I mean by discriminate here, not like prejudice discrimination, but discriminate between students of different abilities. So how well can it sort of tell what the student's ability is? Right? So let's see what happens if A sub j is really big. How does that affect this model?
Highly discriminated?
Yes, it's highly discriminative, but why?
Because even so if the student's ability is slightly away from the test requirement,
Right.
you get really bad odds. I mean, you could get really
bad or good, right? So if the yeah, exactly. So if the student's ability, if theta is only slightly higher than the difficulty of the problem, then you're going to get a very high probability the student answers correctly. And if it's slightly lower, you're going to get a very high probability that the student answers incorrectly. So what that means is that if theta is very close, if theta is on either side of the item's difficulty, you're able to tell if the student is better or worse than that item in some sense, right? If the student's able to succeed on that item or not. Whereas if A is very small, then basically for all values of theta, or like for most values of theta, you're going to get similar probability that the student would answer correctly. So that's sort of a useless item, right? An item that can't discriminate between any students, basically, like if all students sort of have the same probability of answering correctly, then it doesn't help for someone who wants to determine what the student's ability is, right?
So if a certain set of problems are important
Yeah.
to the test taker, then he would assign higher AJ so that he wants to.
No, sorry. Okay, that's a great question. AJ is assumed to be like a feature of the item. So once you design an item, it has some discrimination ability, and you want to infer what that is. So let's look at just the visualization of this. So here's a plot that shows the sort of the logistic curve. There's one difference. This is actually for the 3-parameter model, which I'm not going to go into today. But basically what that third parameter is a C. And what that says is that the student has some probability of guessing. So if it's a multiple choice exam, maybe you would say if there's four choices, you might say the student has a 0.25 probability of guessing. So this is sort of the lower bound of the student's performance. In actuality, some problems that are tricky, if you're trying to get it right, sometimes you'll do worse than guessing. So even this isn't a perfect assumption, but it might be a reasonable assumption. But we're going to ignore that assumption for now. So what the B parameter does is it says where your where the center of your logistic curve is. So basically what this means here, if B equals 0, it's saying that for students who have a theta of 0, they have a 0.5 probability of getting the question correct. Right? So what happens if we increase B? So let's say B was 2. What would that mean? Like what's a statement you can make with that? Okay, the curve would shift. Which student would have a 50% probability of answering that question correctly if B equals 2?
For theta equals 2.
Yeah. So whatever your B parameter is, basically one thing you can tell from that is a student with a theta of that exact same value has a 50% chance of answering the question correctly, and a student with a higher theta has a higher probability of answering correctly, and a student with a lower theta has a lower probability of answering correctly. And the A parameter sort of determines the slope of the curve. So A equals 1, sort of a standard logistic curve. If you increase A, basically you get like a curve that just spikes at some point. And if you decrease A, you sort of get like a line, or actually you get something pretty flat, basically. Does that make sense? Yeah.
How do you relate what values A would take to the difficulty of the problem, or what the?
So they're assumed to be just different parameters of a problem. You could have a very difficult problem. So imagine you have a very difficult problem. So like let's say B equals 3, right?
What do you mean by that? If the student's skill is slightly different from
Yeah.
the requirement of the problem, then the score goes.
Right, so I'll give you an example. So let's say B equals 3 for some problem. So it's a very hard problem. But the only students who aren't at that level basically have no idea what they're doing, so they answer incorrectly. And students who are just above that ability completely understand it, and they'll have a probability of 1 answering correctly. That would be like infinite discrimination, right? Does that make sense? So that's not a measure of the difficulty. You could have a difficult problem that some students are just capable of guessing. Like as your ability increases, you have a better sense of what you're doing. But for some problems, like you just have no idea if you don't know it, and you like completely got it. Like you're assuming there's sort of like it clicks or it doesn't, and that could be for any level of difficulty. Does that make sense? That's a great question. So these are assumed to be two separate parameters. Like presumably you can have items that have any pair of B and A parameters, any difficulty or discrimination. And these are parameters that we want to infer from our data. So when we design a problem, we don't necessarily know what it is. So we're going to use this sort of logistic model to infer these parameters, as well as the student ability parameters. So this is useful for testing. So IRT is going to be useful for testing for a number of reasons. Before I go into that, I'm going to give you guys a poll. This is basically almost like identical to the poll I gave last time about the AFM model. Actually, pretty much identical. So except I fixed the typo we had before. So just sort of to see if you remember what from last time. So let me activate the poll.
Cheyenne?
Yes.
While we're waiting for us to answer, did you upload the slides by chance?
Oh, I could do that. Would it be? Oh, sorry. Let's see.
Yeah.
I don't know if I have that. Okay, they should be uploaded, but you have to manually type the URL, which is change it. You can go to the 25 slides and make it 26. Okay. I'm not going to change the website right now. Is everyone done with the poll? 10 more seconds, sure. I guess this is a difficult problem. Or there's technical difficulties. Done? Okay. All right, let's see. Okay, so almost vast majority of you thought it is a logistic regression model, which is true. I think I probably mentioned that several times over the course of the lecture, which is good. Again, before, I mean, this is sort of a, you can go either way. It is a linear regression model, but I didn't tell you linear regression model with, with respect to what, like outcome variable, but it is a linear regression model if you take the log odds as the outcome variable. Same as before. But it doesn't follow either law of practice, because the law of practice, what does that mean? It means you're learning, right? So if you remember from last time, the law of practice always correlates some outcome variable with t, where t is the number of trials you have to practice. These models assume no learning, so it was sort of a trick, somewhat of a trick question, because it doesn't assume any law of practice, because it's just measuring a student's ability. Does that make sense? Student is assumed to not be learning in this setup. Okay? Okay. So what are some of the advantages of IRT over what's called classical testing theory? And classical testing theory is basically what was developed in psychometrics before IRT, which is basically when you give in a test, you just sort of add up the scores of each of the tests, and then you can use some models like linear regression models to predict a student's performance. So basically, what are the advantages of IRT over just, basically adding up the items, adding up the score of the student on each item of a test? Why use this more sophisticated model? So what do you guys think? Any ideas? What does IRT give us over just, computing the score directly? Like, how we computed your midterm score. Why use an IRT model instead? Yeah?
A student that might understand a concept may still get the answer wrong, and I think IRT, like, since it's based on your probability, knowing like your ability and things like that, it would like more accurately reflect how much the student knows as opposed to answer correctly.
Right. So you're saying that like we're sort of disentangling sort of the student's actual ability and sort of whether they answer things correctly or not, which has some noise, right? Yeah.
So in the IRT setting, what does the PIJ?
It's the probability. Sorry, it's the probability of a student answering item J correctly. Probability is.
Item J is the entire test, right?
No, sorry. Item J is one problem. An item is a problem on a test. So how you would compute the score if you wanted to, you could, well.
You would do like an expectation over the marks for that times the probability of the student.
So often, I don't know if you'd actually want to necessarily compute a score. You'd actually want, if you can, okay. So how would an IRT model be used is a question. One way to use it, for example, is you have a student working on a test. Initially, let's assume we know nothing about the student, right? So let's say we're administering like a GRE exam. For the student, we don't know anything about them, let's say. So what do? We give them a problem. We see how well they do. And then we can sort of estimate what we think their theta parameters from that. And the more problems we give, we can get a better estimate of their ability. So that ability, in essence, you can think of as the score on the test. Because if that's what we care about. If we care about sort of measuring a student's ability, and we're assuming there's one fixed ability, then that could be the student's score on the test. Does that make sense? Okay. So these are some of the, sort of the right intuitions. So one thing is that we can measure with much more precision. So we can measure a student's score with a lot more precision than on a classical test. So let's say we have a 10-item test, right? And let's say each item we assign a value of 1 to each item, and then we grade the student scores as we would normally. How many different scores can we give to students? And there's no partial credit.
Number of problems.
Yeah, or number of problems plus 1, right? So we can give 11 different scores to students. Now, what if we're using item response theory to sort of measure their ability? So basically, how many different student abilities can we measure from a 10-item test? Potentially. What? Well, if we're using sort of, okay, the student's ability can take on any real value, but if we're sort of estimating it just based on using the model, and we only give them 10 items, there's only a fixed number of scenarios that can happen, right? We know nothing about the student. How many sort of different scenarios can happen on the test that could lead to different possible measurements? 1,000? Why? Yeah, exactly, 2 to the 10, right? Because a student can either answer each question correct or incorrect, and based on that, each item's difficulty, if each item has a different difficulty, and let's say different discrimination, then each item will give us different amounts of information. So for each item, based on the binary, whether the student gets it correct or incorrect, we sort of end up with a tree that we have like 1,024 different leaves, which can give us a different theta for each, different values of theta that we can measure. So we can measure about 1,000 different scores for students rather than just 10. Does that make sense? So it sort of gives us more precision. Any questions about that? Okay.
If the student gets it or not, that still doesn't get you anything, because the theta maps to the probability of the student getting it right. How would you still map from that to a theta value? So there's a chance, some chance that the student may get the question right based on.
Yes. So how do you get the? We're gonna actually talk about that in a bit. But basically, what you do is you do like a maximum likelihood estimation. So once you've seen a student do several problems, you can find what's the theta, the maximum likelihood theta. And if you had some prior estimate of the theta value, then you can use like some sort of Bayesian. You can find the map estimate, like the maximum a posteriori. Does that make sense? So we use just sort of the standard things we do in machine learning to try to estimate what the student's ability is, given this model. Another thing we can do that we can obtain like a standard error of measurement, which is basically sort of like a confidence interval over the student's ability. And we can't typically do this using a standard test. I mean, there might be different methods of doing it, but this is a more sort of clear way of doing this. So this is useful because when we're doing a test, we can sort of see, how confident are we over the student's ability, and we can sort of keep giving problems till we get, as precise as we want. So it allows for that as well. Another advantage it has is we can give different tests to different students without sort of compromising the ranking. So maybe for you, maybe because I'm concerned about cheating, I want to administer different tests to each student, and those tests might be composed of different items. But if I've estimated accurately what the items' parameters are, then I can sort of equate different tests using the IRT model. And I'm not going to go into that in detail, but this is what's typically done in like when like for example the GRE exam, they have to equate different tests because not all students are going to get the same test, right? Otherwise, you can go tell your friends what the questions were, and that would compromise the test. And the last thing which I'm going to focus on is computerized adaptive testing. So we can make tests adaptive. So why would we want a test to be adaptive? So have you guys ever heard about adaptive testing? You've probably taken an adaptive test. Probably all of you have taken the GRE, which is an adaptive test. But you might have not known that. So why might we want to make a test adaptive? So let's imagine, yeah, okay, sorry.
So if you're giving new problems, if you're not learning anything more about the student's ability, like the problem's too easy, then it's not really worth giving that problem.
Right. Yeah, so for example, let's say we have a really good student, right? And the student's just answering all the questions on our test correctly, so they're likely to get 100%. We have another really good student, so they get 100% on our test. But which student is better than the other? We can't tell that using a standard test if we don't have very hard problems, right? And if we do put very hard problems, let's say we have two students that aren't doing well on most of the problems of the test, giving them hard problems is useless because we already know that they're not doing easier problems, right? Does that make sense? So it's actually I think it's a pretty clever idea of sort of adaptively choosing what problem to give to students to try to get a better measurement of their ability. And presumably you're going to spend less time because you minimize the number of problems to get the same level of precision. Otherwise, you might have to give a ton of problems of different levels of ability, and you're sort of wasting the student's time and wasting resources in doing so. So the idea behind this is we start with a calibrated set of test items. So what I mean by calibrated is we sort of calibrated we've measured the parameters of those test items. So how might we do that? Any ideas? How can we measure like the difficulty and the discrimination parameter on some test items? So we just administer the test to a bunch of students, and we use the IRT model to measure those parameters. So these might be students, sort of like a pilot study, right? And one thing that's done often, like for example, at least I know the SAT, and I think the GRE might do this, that they give one section of the exam is sort of called experimental, and it won't be counted for your score, but you don't know which section that is. So why they do this is they're trying to give new questions to calibrate the parameters of those items. Does that make sense? So now maybe if you've taken these tests and you never knew how they really work, you just heard these mystery things, now it's sort of making sense why they're doing these things. Because when I was taking these tests, I was like, I don't know what it means for it to be adaptive. Actually, the GRE, just as a side note, was changed. It used to be item level adaptive. So every item was determined adaptively based on how you've done so far. They changed it, I think, in 2011. So probably before any of us have taken it. So now it's section level adaptive. So the first section, all the problems are sort of fixed, but the second section is adaptively chosen based on how you do the first section. I don't actually know why they did that. So if anyone knows, that would be interesting. OK, so then what we do is once we have these set of items, based on our estimate of a student's ability, so theta hat, what we think the student's ability is so far, we choose the item that will give us the most information to get a more precise measure of the student's ability. Does that make sense? So if we know the student's really good, we might decide, OK, let's give an item with high difficulty, because we want to see if the student will answer that as well, and be able to answer that correctly or not. If the student's doing really poorly, we might say, OK, let's give an item of low difficulty, because we want to know if the student will be able to answer that. Given an item of high difficulty wouldn't give us any information. Then the student answers the question, so we know if they got it right or wrong, and then we update our estimate of theta hat using maximum likelihood estimation. So naively, like at each time step, we would just run the model again. We would run like our equations again to find what the maximum likelihood estimate of theta hat is. And then we keep repeating these until termination. And we can decide when to terminate based on a number of considerations. Maybe we have a fixed number of problems that we want to administer, or maybe we want to get to a certain level of precision. And so we keep giving items until we reach that level of precision. Does that make sense? OK. So how do we measure information? I'm not going to go too much into detail on this, but there's what's called Fisher information. So this is something from statistics developed by the famous statistician Fisher. And basically, this is the formula for it. Again, I'm not going to go into the details of this. I just put it up here. But this is what the information would be in the case of the one parameter IRT model. So the information that we can get for item J, so information for item J for a student of with ability theta sub I is this here. So what does this mean? This means it's the probability that the student answers item J correctly times the probability that they answer incorrectly. So that's sort of how much information we can. And we can derive this. You can derive this using the formula for IRT, plug into here. So if you want to do that at home, go for it. But so that's what it is. And for a 2-parameter logistic model, for a 2-parameter IRT model, the information is the same, but we multiply by the discrimination squared. So this sort of makes sense, right? Because if an item is very discriminatory, then we should get a lot more information from giving that item, right? OK, so how do we use this in practice? So here is sort of a set of curves, information curves. So this is the information plotted. The x-axis should be theta, and the y-axis is the information that it gives. And each of these curves is for a different item. Now it sort of has like a bell curve type shape. That's just sort of, if you plot the information, that's just how it will end up looking. And then, so each item has a different, different sort of information curve. So how do we use this information to determine what problem to give to a student? So let's say initially we just say the student's parameter we assume is 0 to start with. What problem should we give next to that student? I think I hear some people saying it. 6? Why 6?
That theta here has the highest information about how good your estimate is.
Yeah. So basically, you just look, OK, at that value, you look at where it intersects each of the curves. So for 7, it intersects here. For a lot of these curves, it's basically no information. But for 6, it gives us the most information. So we give problem 6. And then we refine our estimate of theta by finding the maximum likelihood estimate. Let's say the student gets it wrong, so it ends up somewhere over here. Then we look, OK, maybe 2 gives us the most information. So we give item 2. And then we repeat this process. Does that make sense? And intuitively, this should make sense, right? Because item 1 is it's sort of the mean of this item is the difficulty, right? So if this item is a very easy problem, if we think our student's ability is much higher than that, giving an easy problem gives us little information about the student, because they're most likely going to get it correct. That doesn't really tell us anything. OK? Any questions about this? OK, so that's all I'm going to talk about computerized adaptive testing. It's interesting. This isn't a topic that's typically, it's not considered part of AI, but I think it is AI. So I think it's a sort of a nice application because it not only uses machine learning, but also uses adaptivity. And actually one interesting thing about this form of adaptivity is we're sort of doing something very greedy, right? At each time we're deciding what's the best thing to give to the student. Well, would it be useful if we could sort of look ahead and say, well, I know I'm going to give 10 problems to the student. What's the best sequence of 10 problems to give? Would that give us any more information? Rather than doing something very greedy like this. It turns out it wouldn't, because the information actually is additive. So the information for every problem we give, you can add up the information. So giving sort of the problem we think would give us the most information next is, I guess, the best thing to do under the model. So doing something greedy in this case is very nice. Next time, I'm going to briefly talk about adaptivity when we're trying to instruct students. And in that case, it's not so clear that giving a problem to a student greedily is best. Maybe we want to think about what's the next sequence of 10 problems we should give to the student to enhance their educational experience the most, right? But in this case, it's a very sort of simple form of adaptivity, but it could sort of go a long way. And this has been used in many tests. So many of the like the GRE, the GMAT for going into business, getting admitted to business schools, and many of these examinations actually use this computerized adaptive testing. So it's sort of it's a very prevalently used application, which is nice. OK, so now I'm going to shift gears to another sort of application. This is sort of just a recent paper from last year. It was at a conference called Educational Data Mining that I thought was sort of a nice application of assessment and also involves some mechanism design, which we've learned about. So I thought it was pretty cool to cover. So the question, I guess, is how do we grade free-form questions in large courses? For example, MOOCs, massive open online courses. So we might have thousands of students. We don't have enough instructors or TAs, to grade every student's assignments. So how do we get about this grading? So what are some ideas? So one common approach taken in these courses is to use peer grading. So you pick, maybe a random student in the course, and you say, okay, you grade this other student's problem, or maybe it's an essay, maybe it's not a problem, maybe it's like a free-form essay, and you might give them a rubric to do that grading. And there's been lots of results that say, okay, there's some correlation between a peer's grade and an instructor's grade, and it's still useful for the student because it gives them feedback and things like that. But here we're going to investigate maybe a more interesting or a different type of grading, which is self-grading. So you grade your own problem. And so what we're going to do is we're going to ask the student how likely they think they are that they answer the question correctly, right? So one way to do it is to give a student a rubric and have them grade according to that, right? But let's say this is even more, a more open-ended question or more free-form question, and we don't necessarily have a rubric for the question. And so we just want to say, okay, ask the student how likely they are that they answer the question correctly. Because presumably the student has some measure of knowledge about their own ability, right? And we sort of want to tap into that. Now, again, this is an assumption. Maybe you think the student doesn't really know their own ability well. But let's assume they do for now. So how can we sort of tap into that? So we want, another question is we want a strategy proof mechanism to sort of elicit a student's correctness, how likely they are to answer a question correctly. So we can sort of think about this as a game, but it's a game with just a single player. It's just the student. And we want to just make sure that the student gives us an honest answer, right? Because maybe the student can say, oh, I think I answered this question very correctly. And if we're going to use that to say, oh, OK, then you probably did, then obviously the student has incentive. If they're not a very honest person, they have incentive to lie, right? So we want to come up with a mechanism that disincentivizes the student from lying. OK? Is the setup clear here? OK. So here's one thing we can use. And this is a quadratic scoring rule, which it's been used, I think, for decades in different settings. So the idea is that S sub ij is going to be the score we assign the student I on item j. Okay? So this is going to be what score we give them. So presumably the student wants to maximize the score. That's the assumption here. And we're going to say that if item j is actually correct, we're going to give the student score C sub ij, where C is sort of what the student tells us is their confidence, or what the student basically, we ask the student, how likely do you think you got this question correct? Or not how likely. We just ask the student to give a score on the problem. Okay? And we'll see what the score corresponds to. And they give us this score C. If they got the question correct, we give them the score that they gave us. Right? If they got it incorrect, though, we penalize them. We penalize them by giving them half of the square of their score. So it's a pretty harsh penalization. Yeah?
It's like, if there is a very simple problem and I got it, I will put like a little high score to the problem.
Yeah.
Yeah.
Oh.
I mean,
you're asking for the intuition for what you do?
No.
Oh.
It's like I'm asking. So what this score Cij corresponds to?
I'll go into that. Yeah.
I mean, if you formalize it as I want to maximize my score, that I will put a really high score to the problem that I'm pretty sure I get.
Yeah. That's the intuition behind what we want.
Oh, it's okay.
Yeah. So if the student is confident they did well, they're going to assign a high score for themselves, so they get a high score.
Oh, okay.
If they think they did poorly, they're not going to want to do that, because then they're going to get a very large penalty. So they're going to lower their score. So we're going to see why we chose this mechanism, or why we might want to choose this mechanism. So the idea is that the student wants to maximize their expected total score, right? And what the expected score is that if they answer correctly, so with probability Pij, they're going to get Cij for their score. And if they answer incorrectly, they're going to get negative 1/2 Cij squared, right? And so if we just maximize, we can figure out what Cij would the student give to maximize this score, right? And if we do that, we find that the student it's maximized when Cij equals Pij over 1 minus Pij. So basically, this is the odds that the student answered the question correctly. So it sort of has to do with their confidence about how correct it would be, right? So this is why we might want to do this mechanism, because we would get an honest answer for sort of the odds that the student thinks they answer the question correctly. And this is, of course, relying on an assumption the student would know what Pij is. The student knows how likely they are to answer correctly. In practice, they don't. But we're going to make another assumption, which, again, it's debatable how accurate this assumption is, but let's just go with it. We're going to make the assumption the student is going to solve an IRT model in their head. Okay, it might be true. I don't know. We have to ask the psychologist if this is what students do, right? So Pij here is the student i's estimated probability to answer the question correctly, right? Theta hat sub I is the student i's estimate of their own ability. So what the student thinks their own ability is, and B hat j is the student i's estimate of the difficulty of item j. Now I think it might be more realistic to assume that the student has a measure of how likely they are to answer the question correctly, but somehow there's these latent estimate and problem difficulty that sort of underlie that student's estimate. But maybe the student doesn't explicitly do any computation in their head that starts from these parameters and then builds their way forward. But the model sort of assumes they do, because the model is going to assume that the difference between the student's ability and the item difficulty is normally distributed, with the mean of the true student ability and item difficulty, the difference between the true parameters. So it's assuming that the student can sort of is sampling, a sort of estimated parameter, which corresponds to the difference between their true ability and the true item difficulty, with some standard deviation, with some variance sigma squared. Okay, does this setup make sense? I mean, I'm not asking you if it's an accurate setup. I mean, I don't know if any of us can judge whether this is actually happening in a student's mind, but let's just assume it does. Okay, so what we have here, let's say we want to estimate these parameters. So remember that C sub ij, given our mechanism, is equivalent to the odds of the student answering correctly versus answering incorrectly. So if we take the log of C sub ij, it's equivalent to the log odds, which is equivalent to, we can treat it as being equivalent to the true student's ability minus the true item difficulty plus some noise epsilon, which is sampled from a normal distribution with mean 0 and variance sigma squared. Does that make sense how we got from here to here? Is that a hint? No. Okay? So how might we now estimate the student's ability from this? So we know what Cij is, right? Because we elicited that from the student. So we can measure the log of it. So how might we estimate the students? So now let's say we've done this with many students on many items. So we have sort of a matrix of students and items. How might we now estimate the parameters for this model? Yeah?
Just run maximum likelihood, which in this case, I guess, is just linear regression.
Yeah, exactly. So it's just a linear regression model. So we can find the maximum likelihood estimates of that model. Does it make sense why it's a linear regression? It's just the same thing we've seen before. So the way to actually write this out is the theta sub I, you're going to have a parameter for all students. And then you're going to have a variable, like a dummy variable for each student and say, is this student I or not? So then for student I, you end up only having theta sub I. And again, for the items, you're going to have a variable for all items. And you're going to say, you're going to have a parameter for all items in the linear regression model. And then you'll have a dummy variable that says, is this item j or not? Okay? So we can do this simply using linear regression. Yeah. Okay, so now I'm going to give a poll. Okay, so one question is, though, so this might be a great mechanism. One question is this mechanism fair? What do I mean by fair? I mean, would it give us sort of the same result as if we had given the student a standard test and we graded their question in the standard way, right? Does that make sense? So if we graded their items ourselves, in expectation, is our grade going to correspond to the grade that this mechanism would give to the student? So either you think, yes, it is fair, or no, it's going to inflate scores of students with higher ability and deflate scores for students with lower ability. Or no, it's going to deflate scores of students with higher ability and inflate scores of students with lower ability. But I'm going to there's going to be a little trick to this, which is, I'm going to make this a meta poll. You're also going to give me the confidence of your answer. Just to make this more fun. But I'm not grading this according to any mechanism, so.
So again, how our grading of the student works? So
yes, when you grade it, you just grade it correct or incorrect. And you assume that's perfect grading. But in okay, actually. Let's just say you grade, you accurately, okay. To make this more concrete, let's just say you compare it to P sub ij.
To P sub ij.
Yeah, because that's sort of the expected student's grade, right?
Yes, yeah.
So you want to compare it to that. Because if it was fair, then in expectation, the mechanism is going to give, would give a score of p sub ij, right? Does that make sense? According to this notion of fairness. Okay. Is anyone still working? Okay, 10 more seconds. This question's a little harder because you also have to measure your confidence. But so I know you're all solving your IRT models.
And then you estimate those parameters for next year.
Yeah. Okay. Let's see. Okay. So let's see, how do we interpret this? So the people who are most confident thought it will inflate scores of higher ability students. And the people who are less confident thought it's fair. Interesting. Because this gives us more information than normal. Okay, so let's, I guess it makes sense to ask the people who are most confident. So why did you think it will inflate the scores of higher ability students and deflate scores of lower ability students? Someone explain?
It punish more when the student answers the
let's look at
the answers wrong. Like if you answer the question wrong, you get more punishment from this formula. So it tends to deflate scores to lower ability students.
Okay.
Yeah.
Does anyone have another explanation, or want to contest that? There were some high confidence people for, I guess all of. No, not for the yes, but there were some high confidence people who thought the opposite, that it's going to deflate scores for high ability students. So those highly confident people, do you want to justify your answer? Or maybe you measured your confidence inaccurately, or it could be due to the variance in the normal distribution, right? Okay. Well, okay. So let's think about this. So C sub ij, what was that under this mechanism? Yeah, but what score did we elicit from the students, given the mechanism? The odds. Yeah. Right. So if we plug that in, what do we get? I'm assuming some of you might have done the math. What? Somebody's saying something. Yeah.
Like a little half squared plus half pi to the third.
Plus half pi to the third.
I think it will be just half pi squared divided by 1 minus pi.
Yeah. Okay. So let's do it. So we get so the first expression. Sorry, I don't have a board. We get pi squared over 1 minus pi, right? Because it's the odds, right? So from the first side we get that. The second we get pi squared over 1 minus pi again. 1/2 pi squared over 1 minus pi. Does that make sense? And so when we do, we get 1/2 pi squared over 1 minus pi. Okay. So now let's think about this. Really useful to have a board. Okay. So what does this mean? This means, okay, let's say a student is very high ability. So what does that tell us? Yeah, the Pij is high. Okay, so let's say it's close to 1. Let's say it's 0.9. Okay, so if we do 1/2 0.9 squared over 0.1, is that greater or less than 0.9? Right, because 0.9 is what it would be if it was fair. It's greater? Less? You could just plug it into your computer. But yeah, it should be greater, right? Okay, so that means it's going to inflate a score with higher ability. Now let's do the opposite. Let's choose a student with a low ability. So let's say they have a 0.1 probability of answering correctly. We're going to get 1/2 0.1 squared over 0.9. Right? Let's make the 0.9 a 1. Okay, so it's 1/2 0.1 squared, which is much less than 0.1, right? So we're really deflating the score for a student who has low ability. So is this mechanism fair? No. So it's actually it's widening the achievement gap, which is pretty bad, I would say. I don't think this was explored in the paper. I was just thinking about this. I was like, well, ideally you'd probably want a fair mechanism, right? But this mechanism is not. So this mechanism does incentivize students to give you the information you want, but then you're sort of widening the achievement gap in some sense, which is probably not a good thing. So this just sort of goes to show that you probably want to consider multiple things when you're designing a mechanism, not just strategy proofness per se. Does that make sense? Okay. And we got to see a little bit about how confident you guys were. So I guess the mode was that the right answer had the highest confident people, which is good. So that's a good outcome. Okay, so there's something else that's sort of strange about this mechanism. Has anyone spotted it yet?
Can I just ask a question about the previous result?
Yes, go ahead.
So we want to maximize this score.
Yeah.
And that's why students will give us a fair answer, so that's fine. But then as an output for their actual score for the test, we are not obliged to put this score, we can put any other quantity that will actually fairly measure their ability. The non-fairness here comes from the fact that we have this p squared maybe.
Yeah.
So then we can apply some function to this score s, and then that score will be fair and will not.
Okay, but if the students know you're going to do that, then they might give you a different.
Yeah, but then if this function is actually monotonic, so if it preserves the order, but then it will just curve the scores back. Right now we are curving the scores to the end of the segment. So if we curve it back,
but even then, you're basically changing this function. So a student who knows that is going to maximize their expected score differently, right? Presumably you're going to get a different result.
But it's not modified, right? It's inflating for the higher ability students and inflating.
I think he's saying apply some sort of monotonic. Oh. Yeah. I mean, it's good if you have any points about this, because I sort of thought about this myself. This was not in the paper, so there might be some ways to correct for this. And that'll be interesting to think about. Can you come up with a fair mechanism in this setting that sort of is strategy proof, maybe eliciting sort of a different response, but still is fair? That would be interesting. So if you come up with that, you could probably maybe publish a paper about that. So maybe, I don't know. Okay. Any more questions about this? So there's something else that's weird about this mechanism. How did we incentivize students to give the right answer? Sorry?
By penalizing them if they give the wrong.
Right, but how do we know if they give the wrong answer? We need to grade it, right? But the whole motivation was that we didn't want to grade it, right? Okay, so what happens if we actually don't grade student answers? Then everything falls apart. If the students know that, then they're going to give us, they could give us, untruthful responses, right? See, you got to think about a lot of things here. I guess the issue is we don't want to grade all the student answers, but in order to incentivize people to be truthful, what if we grade some of the student answers correctly, right? We may need to do that. I mean, one thing we could do is we could tell the students, if we grade this is what happens, and then hope that the students assume we grade it. But that's not very credible if they know why we're doing this, and if they have past data that we didn't grade it, then yeah, again, they're not going to believe that probably. Okay, so let's say each item is graded with probability rho, right? For any student. So for any item student pair, for any IJ pair, we randomly determine with probability rho to grade that problem. So now the expected score is going to be this. With probability rho, it's going to be the same score as before, right? And with probability 1 minus rho, it's going to be whatever the student gave us. So whatever score the student told us, Cij. That make sense? So with probability 1 minus rho, the student's not going to be penalized because we didn't grade it, and we have to assume that they got it correct. Of course, we can't assume they got it incorrect. That wouldn't be fair. Okay. So what happens in this setting? So I'm not going to. I think it's now harder to maximize this. You can come up with an equation, but I think it's more illustrative if we just look at what the plots look like. So here are plots. So we're plotting the difference in the student's ability and the item difficulty versus the optimal self-score that the student gives. I guess here's the log of the self-score. So the log of the student score should be in the setting where we grade everything, or the student thinks we're grading everything, it's going to be a straight line, right? When we're plotting it with respect to the difference between the ability and the difficulty, right? So that's why if rho is 1, we have a straight line. Does that make sense? Okay. Now if we lower rho, what happens? So if we set rho to be 0.5, we end up approximating a straight line at some point, right? But before that, it sort of flattens out. So what this says is that students who have a low ability are more likely to give us a higher score than in practice, because they know there's a probability we won't grade it, so they can give us a higher score and sort of get away with it. Yeah. What are you thinking of? I don't think we should apply this mechanism. Okay. And then if rho is 0.1, the situation gets even worse, right? It takes even longer before it sort of approximates that linear curve. And once it starts approximating the linear curve, we're okay, because the gap, if the gap is sort of constant, it's like log of, I can't remember, but log of 1 over p, something like that. So we can measure that. But it's in this regime that we can't, right? So for low performing students, we can't get an accurate measure of their ability using this mechanism if rho is small, right? And even rho is 0.1, that's a pretty small, that's pretty large if we have a lot of students, right? So if we have 1 million students and we have to grade like 100,000 of their students' work, that's only cutting us, by a factor of 10, which isn't that much in that setting. So there's sort of limitations to this, but I think it's still a pretty interesting setup. But does anyone have an idea of how we might correct for this? How we might correct for this? So what can we do? So the problem here is that we sort of have, we can't really measure the ability of students who are sort of in this regime here. How might we get around that or modify our procedure? I mean, can we do something adaptive to help?
I mean, so right now in this setting, when we write the test, we actually can pretty accurately measure the score of the very good student.
Yeah.
So then for other students that are left, we run another test which is easier and then measure and etc.
Yeah, potentially. Or we can do adaptive even at a more granular level, like item level adaptive. So I haven't thought about this concretely, but you can do some form of computerized adaptive testing to avoid this scenario. So that would also be an interesting sort of future direction for this work. Okay? So any questions about this calibrated self-assessment? I sort of motivated as an interesting application, but then I gave you all these problems with it. But that leads to open directions. I mean, this is a work that was just published last year. It was actually won a Best Paper Award, Best Student Paper. And I think it's a pretty clever approach, even though it has these problems. But I think if there's more work done to get around these problems, it could be beneficial. I mean, and there's more reasons to do self-grading. I just talked about the motivation of instructor can't grade everything, but maybe there's benefit for the student to have to grade their own work, right? Because it gets the student, it could help like metacognitive abilities. Right now, I asked you guys what your confidence was. I don't know if that helped you at all, but it might help you sort of better be able to gauge how confident you are, and that could help the student later on. So you might want to do self-grading for other reasons as well, in which case this becomes more important. So you had a question?
If we use an adaptive grading for the lower, performing your lower ability students,
Yeah.
Does that mean that they're capped at a lower overall score, or does that fall out through the like difficulty? Like how does my question? I'm not phrasing it very well. But.
Actually, so I think what you'd sort of want to do is, for these low-performing students, you'd want to grade more of their problems. So let's say we can be adaptive with respect to row, right? We can start with a very small row. We can capture all the high-performing students. I don't know if this is a great idea, but let's just think about what will happen. You can capture all the high-performing students, and then you can say, okay, now for the rest of the students, let's lower row. And you can, increase row. Yeah, increase row, right? And then you can get more students that way. Does that make sense? And you can keep going. And for some students, you might need a very large row, but maybe hopefully that's only a small amount of students.
Before we find out changing the difficulty of questions, is that right with the adaptive?
Yes, in the previous setting. Yeah, so this is a different form of adaptivity. A very good point, yeah. I mean, there might be other adaptive ways to deal with this. Well, one way is just to change row adaptively.
I mean, we can also change the difficulty of the problem as well, right?
You
Because like
Yeah.
here, like this zero on the plot is that when the student ability corresponds to the that difficulty of the problem.
Yeah, that's a good point. Yeah.
Below the BJ, you
Yeah.
also get those.
Yeah, that's true. So yeah, for a student that's out here, if you give them like a BJ, that's like 4 or less, let's say, because let's assume you've measured the item difficulties well, then you sort of have a sense for what the item difficulties are. So then you can determine how much to lower the item difficulty to capture that student. Yeah, so there's 2 different ways to do this adaptively. And I think both would be interesting to see which one gives you more gains. Maybe that's actually better. Any more questions about this? And actually, in the paper, they did some sort of simulations where they basically, I think Ariel talked about Amazon Mechanical Turk, where you can sort of hire like these people to do your tasks. They give them like simple math exams where they actually had to, they implemented this mechanism basically, and they showed how well they can sort of measure. What they were looking at was how well you can measure the rank of the, so they did multiple choice questions, so you can actually have ground truth. So you can rank each of the students, I guess, according to how well they did on the exam, and then you can see how well this mechanism ranks. And they found that like, it's hard to exactly know how good the results are, but there is some correlation between the rankings. So I'll just leave it at that. So it is able to capture, high-performing students and low-performing students, but it still does have a lot of error. Yeah.
Do you mean that we will keep the score of some high-performing students and maybe regrade the score of low-performing students?
Not regrade, but give them more questions.
Yeah, I'm just wondering
Yeah.
whether if the student is told about this mechanism, whether they will behave differently, say the shape of the curve will change.
So this shape of the curve is assuming students know this mechanism, right? Yeah.
But,
Unless I'm missing.
but the shape is an assumption that the student will know something about the regrading mechanism, or
Oh, I see what you're saying. Yeah.
So if you change the hardness of the problem, then these plots will be the same but just shifted. And that's why students still will give those fair, I mean not fair, but like fair according to these plots.
But he's saying that if the students know you're going to adaptively do that, can they game the system even with respect to that? And
No, but
Yeah.
what we know right now is that, let's say, if my ability is 4 in this
Yeah.
setting, I will give you that answer that is pretty close to the ground truth.
yeah.
And then if you shift the difficulty of the problem like there, and like my actual ability is -2, but I still know that the problem's hardness is -4, I will still give
Right.
the fair answer.
Right, but let's say, I mean, I haven't thought about this, but let's say I knew how much they're going to shift it, and do I decide to do something different here, so they shifted a different amount, try to game that, and I haven't thought about that enough to, Does that make sense? If I know, so I guess there's more, you now have more knowledge about what the tester is going to do, and does that lead you to behave differently? I'm not sure. So you're saying if each item is sort of independent, if the student sort of independently deciding what to do in the mechanism, yeah, then the shape would remain the same. But if the student knows that they're being adaptively tested, then maybe it's manipulatable. I haven't thought about that.
I mean, if you assume that this like gray graphics is actually like my best response, that I will still give the best response. Why do I want you to shift this plot more to the left or to the right? Like, there is no point of that.
I think if I'm using the adaptive method, students will not have much adaptive reports low abilities, because if the ability is low, then with hyperability, they will be regraded or be adapted by this.
Well, the regrading isn't necessarily a bad thing, right?
Yeah.
It's not regrading. It's, I mean, so in and of itself, I don't see why students would change it, because then they're just given another problem that's easier for them to handle, and presumably they can get a higher score on that problem, right?
But if they can get a higher score on the EM problem, maybe some students will pretend that.
They don't know it to get a high score later. So you're saying?
Maybe they will pretend that they do not have so strong ability, so that they report lower ability on the first.
Yeah.
But then still, so we will shift the plot even more to the left, but then I will shift it to the extremely easy problems, and you actually can solve all those problems. You still get the true, your truth that lies on this line, the black line. So you just will get a really low score because you're solving the really easy problems.
So I guess the idea is, I'm pretty sure there is a way to adaptively choose problems so the student can't game it. I don't know exactly how you would decide the difficulty based on what you learn. I mean, we could probably work it out. But yeah.
I think if you take the second round, your score cannot beat the person who you think you will get an accurate estimate in the first round. So so they will try the best every single time. If they have more than one try. Does that make sense?
Yeah, I know what you're saying. Yeah.
So that in that way that you won't be gaming the system too much, because if you want to play dumb or something,
yeah,
and you want to try the second time, but your score won't beat if you try the first time.
Yeah, I think that's true. I think if you decide the right questions, you can guarantee that. But if the mechanism designer or the tester gives too easy of a question, too hard a question, maybe then it's manipulatable. I don't know. If they don't optimally choose the right question to give next. But I think the intuition's right. So yeah, it'd be useful to work it out and come up with an adaptive mechanism in this case, and then see how that might perform. At least in simulation, to begin with. So if anyone's interested in that. Okay, any more questions about this? Okay, so I guess to wrap up, as a summary, so we saw that IRT, item response theory, allows for more precise measuring of student abilities than we might be able to do with a classical test, right? Because we're sort of able to measure the student ability, and we're basically using the item difficulty and the item discrimination ability into account when measuring student ability, which we don't typically do when we administer a regular test, right? And this can be used for computerized adaptive testing, and it is used for that. So there's a very concrete application that's used widespread. Whether you like these tests or not, this is an application of AI. I haven't talked about, this is a fun application, but it is an application, right? And we saw how you can use the information to adaptively decide what problem to give next. And then lastly, we saw that we can find an interesting application where we can combine mechanism design with IRT to elicit scores from students. But there's still maybe some work to be done to make this an ideal mechanism, both from a perspective of fairness, and then also what we saw with if the students know the mechanism you're implementing, if they know you're not going to grade things, then they can still manipulate it. So how you get around that. Okay? So I guess we ended up a few minutes early. So next time we're going to talk about applications of AI to instruction, and we're going to introduce a new technique from machine learning called multi-arm bandits. So see you on Monday.